Well, we now come to the next lecture. In the previous lecture, we obtained expressions for the electrical conductivity of the metal, expression for sigma electronic, and we also obtained an expression for the thermal conductivity kappa of the metal, and we also showed that kappa is proportional to this thing sigma electronic times temperature, and the proportionality constant is a Lorentz number which is equal to 3 by 2 kb by E squared. And we also said that the Lorentz number from experiments very closely match the Lorentz number obtained from the fundamental constants, which is kb and E. And in fact, there is a factor of 2 difference, and that factor of 2 difference was later on identified, but when Drude made this comparison, he missed the factor of 2, and that is why the comparison was very close. But if you actually look at the constants and carry out the kappa upon sigma t calculation, what you would get is almost twice the value of the Lorentz number. Well, why is it that the Lorentz number is coming out so beautifully correctly from experiments, even with such very simple assumptions and approximations? There are actually 2 problems with the classical theory of electron gas. Okay. In the classical theory, overestimates the specific heat. So, CV is overestimated by about 100 times CV experimental, CV Drude. Okay. Whereas the velocity of the electrons is underestimated by Drude theory by a factor of 100. That is, V Drude is roughly V experimental divided by 100. V experimental is roughly about 100 times larger than Vd. So, because of that, since we see that the ratio is what that matters, because we have a ratio of Cv to this thing specific heat Cv to the velocity V, it actually cancels. Okay, the error cancels, and that is the reason why you get such a beautiful agreement between theory and experiment. Well, this was one of the most famous successes of Drude's theory, and people were very happy with it until the advent of quantum mechanics, and also because when they looked at other quantities, then there was a problem. What are the other quantities we can look at? The other quantities we can look at are something like thermoelectric power. See, what happens is, when you are looking at a steady state condition and you have got the temperatures of a bar at 2 ends fixed at T1 and T2, then you will have the electrons flowing from the high temperature region to the low temperature region. And because it is no current is flowing in the steady state, what happens is that there is an accumulation of electrons at the T2 end, and there is a depletion of electrons at the T1 end. At the higher temperature end, the electrons are depleted, and the lower temperature end, the electrons are collected. So, which means that a potential is set up which actually counters the diffusion of the electrons in some sense. Okay. So, you have an electric field that is set up which counters this movement of the electrons, and then prevents an electric electric potential it develops, with the electric potential being the one that corresponds to a positive potential at the low temperature end, and a negative potential at the high temperature end. Okay. So, let us see the way you define thermoelectric power is the following. That is, the thermoelectric power is the electric field that you generate because of a temperature gradient, and it is proportional to the temperature gradient, and so the proportionality constant Q is called the thermoelectric, the coefficient of thermoelectric power. It is also called the Seebeck coefficient. Okay. Well, is there a way of actually obtaining an expression for the thermoelectric coefficient of thermoelectric power or the Seebeck coefficient? To do this, let us see what the drift velocity of the electrons is because of the temperature difference. So, if I want to calculate the drift velocity, I can say that the drift velocity Vq due to the temperature difference can actually be written as 1/2 of V at x minus V tau minus V of x plus V tau. Like I said before, that even the velocities are roughly stays same over the length of a mean free path. So, we can assume and write it down in this fashion. So, this can actually be written again by expanding in the Taylor series. We can get this one as V of x, V at x rather, minus V tau dV by dx minus V of x minus V tau dV upon dx. So, this can be written as just equal to minus can be just be written as Vx tau times minus dV by dx, or this can also be written as tau times minus dV squared upon 2 by dx. So, in 3 dimensions, what happens is that you have to take the root mean square velocity along all the 3 components, and what you would get is this is actually equal to minus tau by 6 dV squared upon dt. Okay, here what I have done is to replace d by dx by d by dt times grad t. I have replaced d by dx is equal to d by dt grad t. Having done that, we know that we can always say that this is actually equal to dv squared by dt. So, what we will have is q. We can also now what we can do is now also get the this thing the thermoelectric power. We can equate V of q. This is the drift velocity due to the temperature gradient, and that should actually in the steady state must be equal to minus of the drift velocity due to the field it generates, and this is equal to E tau by m. So, having said this, what we now have is E tau by m is equal to minus, let me see whether the minus sign survives. So this is, yeah, okay, is equal to minus tau by 6 dV squared by dt times grad t, and I know that half mv squared is equal to the kinetic energy. So we have half mv squared is equal to kinetic energy, and we can write down E tau by m is equal to minus tau by 3 d half mv squared by dt times grad t, or we can also write down E is equal to minus m tau by tau goes away on both sides. So what I have is minus m by 3e into half mv squared is the energy, so that's equal to the 3 by 2 RT. So we have half mv squared is equal to 3 by 2 kBt, and so d by dt of half mv squared is actually equal to 3 by 2 kb is what we have, times grad t, or that is going to give me minus m by 3e, this is E, charge of the electron, into 3 by 2 kb will be q. This is equal to, that is actually plus because E is equal to minus, sorry, that will still be minus because sign won't get cancelled. So what we have is, and this will be, the m's will cancel as well because half mv squared I have taken. So because of that the m goes in there, so m will also cancel. So what we have is this will be equal to minus kb by 2e. Okay, so q is equal to minus kb by 2e, and q is equal to minus kb by 2e equal to minus 0.43 into 10 to the minus 4 volts per Kelvin. So now you see that this value is larger, q from Drude's theory is larger than experimental values by almost a factor of 100. So there we have the Drude's theory. This again shows you that there was a cancellation in the case of the Lorentz number, and that's why you got the correct Lorentz number. But the Drude theory is larger by a factor of 100 because the Drude's theory overestimates specific heat. Specific heat is not given by 3 by 2 kb, but it is 100 times smaller than that one. Well, having said this, we still can obtain a lot of information just by using Drude's theory. Like we can actually use the dynamical properties. We can actually compute many of the dynamical properties from Drude's theory. To do this, what we know is that the average time between collisions is tau. So suppose I give you in a time interval dt, dt, the probability of a collision is dt by tau. Okay, so this is just straightforward. So because of that, if I want to look at what happens to the momentum change in going from t to t plus dt, what is the momentum of an electron at time t plus dt given the momentum at time t and acted upon by a force F. First let me write down the equation for that one, and then I will show you how it is comes about. So the momentum at Pt plus dt is actually the probability that the electron does not undergo a collision in the time dt by tau. Okay. So it will continue with the same collision, same momentum as before. So if the probability that it continues with the same momentum as before is 1 minus dt by tau, the momentum at time t, plus of course the impulse due to the force in that period, which is Ft dt. So it is quite simple. I can rearrange this equation to get P of t plus dt minus P of t is equal to minus dt by tau P of t plus f of t dt, or P of t plus dt minus P of t divided by dt is equal to minus P of t by tau plus f of t. In the limit dt tending to 0, this gives me dp by dt is equal to minus p by tau plus f of t. So this is the operating equation for time dependence of the momentum in the presence of an electric field or in the presence of a force f of t acting on the particle. Given this, one can get an expression for AC electrical conductivity of the system. So how does one go about getting the AC electrical conductivity of the system? That's quite simple. What we will do is, let us assume there is an electric field E of t given by E of t is equal to real part of E of omega e to the minus I omega t. So I am looking at a AC electric field as being applied, and then I want to see what happens to the momentum. So we can assume that P of t also has the same time dependence. Has the same time dependence. That is P of t is equal to real part of P of omega e to the minus I omega t. So once we plug this into the equation above, what we will get is the following, that is p omega times minus I omega is equal to minus p omega by tau minus E times omega. So, this is straightforward, and we can write down p omega as minus E omega divided by 1 by tau minus I omega. Now, we know what the current is, j of omega. If I write down j of omega, because we know p of omega, I can write it as minus Ne by m p of omega. So, having written that, I can write, plugging this in, what I will get is j of omega is equal to Ne squared times E omega divided by 1 by tau minus I omega. So, I get sigma omega, which is a frequency dependent conductivity, as equal to Ne squared tau by m divided by 1 minus I omega tau times E of omega. No, sorry, E of omega is not there, because I am writing right away for j sigma omega, and so it will not be there. So, I can actually write this one as sigma naught divided by 1 minus I omega tau. Sigma naught is the 0 frequency, is the DC conductivity, DC coefficient of conductivity. So, I can actually get sigma omega in terms of the real and imaginary parts. So, if I were to do this to get the real and imaginary parts, what I will get will be the following. This is equal to sigma naught divided by 1 minus I omega tau into 1 plus I omega tau, or that is equal to sigma naught into 1 upon 1 plus omega squared tau squared plus I times omega tau divided by 1 plus omega squared tau squared. So, the imaginary part of the sigma omega actually has a Lorentzian kind of distribution, or it behaves like a Lorentzian. From this, with the help of Maxwell's equations, we can get an expression for the dielectric constant. For the frequency dependent dielectric constant. This is something that I will do in the next lecture, and that will actually not only that I will go into epsilon omega, I will also talk about the optical properties of metals at high frequencies, and I will introduce the concept of what are called plasma frequencies, and I will show you why for frequencies above the plasma frequency the metal behaves like a perfect reflector, and below that there will be absorptions at various frequencies, and I will talk about probably those details a little bit later. But for now I am going to stop here, and I will get back to frequency dependent dielectric constant and the plasma excitations in metals in the next lecture. Thank you.